Hello friends, today I will introduce you to three different classes of organic compounds: alcohols, ethers and epoxides. Alcohols are, we can say ROH, this is alcohol. Then we have ether, then epoxide. This is alcohol, this is ether, epoxide. So what is common in these three different organic compounds? There are three different functional groups. One is the OH group, that is the alcohol group is the OH group. OH group, this is the alcohol group. Then we have this OR group, that is ether group. And this is our epoxide here. So three functional groups that contain one CO sigma bond. This is the common factor here. That is three different classes of organic compounds. They containing one CO sigma bond. New functional groups. Three new functional groups are here. Okay. That is a polar bond. Polar CO sigma bond, we can say. Polar CO sigma bond. This is the common characteristic of these three different classes of organic compound. Polar CO sigma bond here. Okay. Now, the reactions of these groups, they follow the same one. That is SN1, SN2, then we have E1, E2, etc. There is no other new mechanism here. The reactions and all we will discuss in detail later. But today it will be only a preliminary introduction to these classes of organic compounds here. Okay, now alcohols. Alcohols contain an OH group. Now, OH group here, it is bonded to a carbon atom. That carbon atom is sp3 hybridized carbon atom. Important point. sp3 hybridized carbon atom, that is OH group, it is bonded to an sp3 hybridized carbon atom here. So alcohols are classified as a primary alcohol, you know that, secondary alcohol, tertiary alcohol, and all this kind of a thing. Okay, now what are these primary alcohol? Primary alcohol means it depends upon the number of R groups, that is the alkyl groups. Okay, so the primary alcohols means, say, that is primary, secondary, tertiary. Three different types of alcohols here. Tertiary, that is primary, say we can write it, say 1, then is a 2, then 3. Okay, it depends upon the R groups, the number of R groups here, alkyl groups here. Okay, the classification is based on the number of carbon atoms bonded to the carbon with the OH group here. Okay, like this, say primary. Primary means how it will represent here, say R, say CH2OH. Correct? Like this here. Now we can say secondary. Secondary will be, say, R2CHOH. This will be a secondary one. R2, say CHOH. That is two R groups are there. Then when you come to tertiary, it will be R3. R3COH. Like this here. You know, these are the classifications here. That is, OH group, it is linked to a carbon atom, which is sp3 hybridized. Now the classification, it is based on the number of carbon atoms bonded to the carbon with the OH group here. Correct? So primary, secondary, tertiary, etc. Now here it is sp3 hybridized carbon atom. Now suppose the OH group, it is linked to an sp2 hybridized carbon atom. What will be the nature of the product here? That this is sp3. These are all sp3 here. Now assuming the carbon atom OH group is linked to an sp2 hybridized carbon atom here. sp2 hybridized carbon atom. So these compounds are known as enols and phenols. Okay, enols and phenols here. Enols have an OH group. It is linked to a carbon-carbon double bond here. That is an sp2 hybridized carbon atom. Then phenol, here it is an OH group. It is linked to a benzene ring. This is the difference here. sp3 hybridized carbon and sp2 hybridized carbon atom. So how will you write this enol? Enols will be, it will look like how the carbon is sp2 hybridized carbon, you know that. So this is, say this is our enol. Okay. Then we have the phenol. So this is phenol, OH group, it is linked to a benzene ring here. Okay, now these compounds, enols and phenols, will be giving different classes of reactions, different types of reactions, unlike the alcohols and ethers and epoxides, etc., which is having a sp3 hybridized carbon atom here. Now, when you come to ether, what is ether? Ethers have got two alkyl groups bonded to an oxygen atom here. So that's our next compound is ether here. Ethers, you know, two alkyl groups bonded to an oxygen atom. That is, they can have symmetrical ether, that is ROR, that is two alkyl groups. This is symmetrical ether. We call it symmetrical ether. Then we have, say, ROR1, that is same type of alkyl groups here. Okay, two different alkyl groups and two same types of alkyl groups here. Two alkyl groups join to an oxygen atom. If the all alkyl groups are the same, similar one, two alkyl groups, same type of alkyl groups, means it's a symmetrical ether. And different alkyl groups bonded to an oxygen atom, these are asymmetrical, symmetrical and asymmetrical ether. Okay, now alcohols and ether, for example, they are derivatives of water, H2O. You can just see it. Okay, how this water, alcohols and ethers, they are organic derivatives. We can say they are organic derivatives of H2O. It is formed by the replacing one or both of the hydrogen atoms on oxygen by R groups. Okay, here in the case of H2O, if you replace this hydrogen atom here by one R group, then or two R groups, like that, you know. So alcohols and ethers are organic derivatives of H2O. It is formed by replacing the one or both hydrogen, we can say, or the hydrogen atoms on oxygen by R groups here. Okay, so that is alcohols and ether here. Now let us see the epoxide here. That will be more interesting. They are also ethers. Epoxides are ethers, but this oxygen atom, it is in a three-membered ring. Correct. So epoxides are also called oxyranes. Epoxides, they are also known as oxyranes. Okay. So they have got a ring here. Oxygen atom is, they are ethers here, the structure of ether. But this oxygen atom, it is in a ring. Inside a ring, three-membered ring here, we can say. Now, when you come to the structure and bonding here, briefly I will just explain to you the alcohols and ethers and epoxides. They all contain an oxygen atom. Okay, this oxygen atom, it is surrounded by two atoms only. Here we can say ROR, we have written here. So this oxygen atom, it is surrounded by only two atoms, and there are two non-bonding pairs of electrons here. Okay, two non-bonding pair of electrons here are alcohol, ROH, if we see. So this is joined to two atoms only, and in the case of ether, it is joined to two atoms here. But on the oxygen we have, okay, two non-bonding pairs of electrons there. Okay, therefore the oxygen atom, it is a tetrahedral one. The geometry of the oxygen atom, it will be tetrahedral. Now only out of the four groups, there are only two atoms around the oxygen atom. There are only two atoms around the oxygen atoms here, alcohols and ethers, and the remaining two are non-bonding pair of electrons there. Okay, therefore alcohols and ethers, they have a bend shape. The structure of the molecule, it is a bend shape, just like H2O. So how it will be a bend shape means how it will look like. The shape of the molecule, it is a bend one. So the geometry of these molecules, say CH3, say this is our alcohol here. Okay, now these are the non-bonding pairs of electrons and two atoms joined to the oxygen atom here. So this bond angle, this is actually 109 degrees here. Bond angle between the carbon, oxygen and hydrogen, that bond angle, that is a tetrahedral, very close to the tetrahedral structure. Tetrahedral is say 109.5 degrees approximately here. So here in the case of alcohol, the bond angle is 109 degree. This sp3 hybridized carbon here. So in the case of say either here, either if we take it CH3, this is either. So here the bond angle, it will be say approximately 111 degrees here. Okay, so the shape is a bend shape. We call it bend shape. Molecule is having a bend shape. Okay, now bond angle is similar to tetrahedral bond angle. Tetrahedral bond angle here. Now this bond angle is the tetrahedral bond angle. Now in the case of an epoxide, there is slight difference here. So how we'll draw this epoxide molecule here? Say oxygen, it is in a three-membered ring here. Then we have the say one hydrogen here, then one above the plane of the ring on a wedge. We can just represent it here like this. So this is, so this is an epoxide here. So in this epoxide here, you know, the carbon oxygen carbon bond, COC bond angle, it is 60 degrees. COC bond angle, it is 60 degree. So what does it imply here? Epoxide COC bond angle, it is, this is the bond angle here. This is 60 degree only. That is, it is a strained molecule. COC bond angle 60 degree means there is strain, angle strain here. So the three-membered ring, there is angle strain because of there is a deviation from the tetrahedral bond angle. Okay, so angle strain, therefore what happens, because of the angle strain, these epoxides are much more reactive than say alcohols and ethers here. That is the difference here. Because of the angle strain, the angle between the C carbon oxygen's carbon bond, the bond angle, it is 60 degree only. There is angle strain. Therefore, these epoxide molecules, they are more reactive compared to alcohols and ethers there. Okay. Now, briefly, I will say, I will take the physical properties here. The physical properties of these alcohols, ethers and epoxides, they all got dipole-dipole interactions there. So because they have a bend structure, because of the bend structure, there is a dipole-dipole interaction. There is a dipole-dipole interaction here because they have a bend structure with two polar bonds there. Okay. Now, alcohols, they are capable of forming hydrogen bonding. You know that is capable of, that is intermolecular hydrogen bonding. Alcohols are capable of forming intermolecular hydrogen bonding because they possess a hydrogen atom on an oxygen atom. Because of that thing, they can form intermolecular hydrogen bonding. Okay, making alcohol, it will be much more polar than ethers and epoxide. Alcohols are more polar compared to ether and epoxide because of the hydrogen bonding here. Correct? With the intermolecular hydrogen bonding, they possess a hydrogen atom on an oxygen atom, and it will be making much more polar there. Therefore, compared to this ethers and epoxide here. Now, steric factors, another thing, affect the extent of hydrogen bonding. You know that you have studied this hydrogen bonding. Steric factors, it will affect the extent of hydrogen bonding. Although all alcohols can, form this hydrogen bonding. So increasing the number of R groups, that is the alkyl substitution around the carbon atom, it will increase, decrease the extent of hydrogen bonding. Correct? That is steric factor. That is known as steric factor. That is, the steric factors affect the extent of hydrogen bonding here. That is, all alcohols can form hydrogen bonding. But the R groups, the number of R groups around the carbon atom, to which the OH group is bonded. Okay, so yes, the number of the R groups increases, the extent of hydrogen bonding, it decreases. Correct? Because of the steric interaction there. That is, the extent of hydrogen bonding decreases as the number of R groups increases. Therefore, what happens? The tertiary alcohols here. That is, the tertiary alcohols. That is the 3 degree we write here. These tertiary alcohols, they are least able to form hydrogen bonding. Okay, tertiary alcohols can they find it very difficult here. They are least able to hydrogen bond. Whereas primary alcohols, we have the primary alcohols are most able to rather form hydrogen bonding here. So the primary, secondary and tertiary of the three, that is the tertiary alcohols are least able to hydrogen bond, whereas the primary alcohols, they are most able to form hydrogen bonds there. Okay, now how will you prepare? Briefly, preparation. I will just change this page. That is synthesis. We will not go very much into the details of this one. That is preparation. So preparation of alcohols, ethers and epoxide. Alcohols and ethers are both, that is a common products of nucleophilic substitution reactions here. It is synthesized from alkyl halides. Alkyl halides, we can represent it here Rx, or we can say this is RCH2X, whatever way you can write here. This is an alkyl halide here. So nucleophilic substitution reactions of an alkyl halide, we can get alcohol here. So what is the type of reaction? This is an SN2 reaction. Correct. Alcohols and ethers are both common products, we can say, of nucleophilic substitution reactions. They are synthesized from alkyl halides here by SN2 reactions. So how this one, we need a strong nucleophile. That is, alkyl halide reacting with a strong nucleophile, it will form an alcohol here and an ether here. Correct. So as in the case of all SN2 reactions we have seen, the highest yields of products, they are obtained with unhindered methyl and primary alkyl halides, not tertiary alkyl halides, because the steric hindrance will be there in that one. So in the case of SN2 reactions here, because the reaction will be an SN2 alkyl halide reacting with a strong nucleophile, therefore methyl alkyl halide and a primary alkyl halide, they will be reacting very fast. Okay, now let us see this reaction. That is, say CH3, we can say CH2Br is an alkyl bromide here, ethyl bromide. So this will be reacting with a strong nucleophile, say OH minus. So this reaction is an SN2 mechanism here. So we will be getting an alcohol here. CH3, CH2, say Br is replaced by, substituted by OH. So we get an alcohol here. Correct. So in the same way, ether, how will you synthesize the ether here? That is, suppose we have this CH3, say CH2, then we can say CH2Cl. Okay, so this will be reacting with a strong nucleophile, or say alkoxide minus here, CH3O minus alkoxide. Again, this is an SN2 mechanism. Reaction will be following an SN2 path or a SN2 mechanism here. So CH3, CH2, CH2, OCH3. So we are getting an unsymmetrical ether here. Okay, unsymmetrical ether. In the same way, we can form a symmetrical ether. Say CH3, we can say CH2Br. Okay, plus alkoxide, we can say is a methoxide here. Instead of methoxide, we can have an ethoxide here. When we are using an ethoxide, we get a symmetrical ether. So CH3, CH2, O, CH2, CH3. Correct? So this is again an ether. That is symmetrical ether and asymmetrical ether, two types of ether. So this is known as Williamson ether synthesis. That is an alkyl halide reacting with a strong nucleophile by an SN2 mechanism forming an ether that is known as Williamson ether synthesis. So Williamson ether synthesis is the most general reaction, we can say, most general method for the preparation of an ether. Okay, so unsymmetrical ether, it can also be prepared in two different ways. Okay, so let us see, we will discuss this one. So what is meant by the Williamson ether synthesis? That is an alkyl bromide reacting with a strong nucleophile by an SN2 mechanism here. It is forming an ether, a symmetrical ether as well as an asymmetrical ether here. We have seen here two different types of ethers can be produced. So this method of preparation, that is the most common method of preparation of ether. That is the synthesis is known as Williamson ether synthesis. Correct. Now, unsymmetrical ethers, it can be prepared in two different ways, but often only one path it will be preferred here. For example, so let us see unsymmetrical ether, how we are going to prepare. I'll just clear this page. Synthesis of unsymmetrical ether. So let us see a compound unsymmetrical ether, isopropyl methyl ether. Let us see how it is being synthesized. Isopropyl methyl ether here. So it can be prepared from in two different ways here. Okay, so we can start with the compound, say Ca3O minus, that is methoxide, correct? And we can say 2-bromopropane. This can react with 2-bromopropane. Methoxide here. So this will be reacting with Br. Then we have this CH. This compound here, this is 2-bromopropane. It is a secondary alkyl halide here. Secondary alkyl halide. So the reaction will be SN2 again. So then this correct. So this will be giving you an ether, that is a isopropyl methyl ether here. So Ca3O, then we have C, okay, isopropyl methyl ether here, Ca3O, CH, Ca3, Ca3 here. This is isopropyl methyl ether here. That we are starting with 2-bromopropane. So this 2-bromopropane, it is a secondary alkyl halide. Correct. This is one mechanism, say one way of preparation of an unsymmetrical ether here, asymmetrical ether here, starting with Ca3O minus. Okay, now instead of that thing, so we can start with bromomethane. Okay, so bromomethane, it is a less hindered alkyl halide. So that will be a preferred path for a SN2 reaction here. Instead of having a secondary 2-bromopropane, we can have Ca3Br here. Ca3Br. So bromomethane, this is a less hindered alkyl halide, the steric hindrance, it is less there. Therefore, it is the preferred path here. Okay, so in the same way, this bromine will go here. Then, so this will be reacting with, say, this alkoxide here. Okay, so this will again give you the same compound, that is isopropyl methyl ether. Isopropyl so this carbon. Okay, so we will be getting Ca3O, same compound here, we will be getting here. So which is the preferred path here? Because where the steric hindrance is less. Okay, so this is the asymmetrical ether here, synthesis of isopropyl methyl ether by using an alkyl halide with a strong base here. Okay, so the preferred path in this case, it will be, the mechanism is a SN2 mechanism. The preferred path uses the less sterically hindered alkyl halide, that is a methyl bromide here. This one, bromomethane or methyl bromide, whatever it is, bromomethane. So this is the preferred path here because of less steric hindrance here. Correct. Now, so these are all this Williamson ether synthesis here. Now, an alcohol, synthesis of an alcohol, that is a hydroxide, hydroxyl group, OH group will be there. Okay, a nucleophile is needed here. So which kind of nucleophile? Say NaOH or potassium hydroxide, whatever it is, for the synthesis of alcohols. So we can see we need an OH group here. For the synthesis of alcohol, an OH group, that is a hydroxyl group, is needed there. That is a nucleophile. So it can be a, say, this OH group, say it can be an NOH or it can be KOH and all this kind of a thing here. Okay, so an alkoxide is needed to make an ether. That is, for an alcohol, we need a nucleophile is needed. That is synthesis of alcohol and OH group. We need a compound containing an OH group. That is just like NaOH and potassium hydroxide here. That is a nucleophile is needed here. But in the case of a ether, this is for alcohol. So in the case of an ether, an alkoxide is needed for the synthesis of ether here. Alkoxide is needed to make an ether here. That is NaO, sodium alkoxide here, or that is sodium methoxide, we can say. Then we can have, say, Na, then O, say, CH2 ethoxide. Okay, NaOCH3, that is sodium methoxide, etc. It is needed. So how will you prepare this one? It's an acid-base reaction again. That is ethanol. Ethanol is reacting with a base. That is how we are getting here. Say CH3, say CH2OH. This is an ethanol. Okay, this ethanol, it is reacting with a base here, say NaH, H minus. That is sodium hydride here. Okay, so which it will be giving you this CH3, CH2, say O minus, Na plus hydrogen. Important point here. Okay, for the synthesis of alkoxides here, For the synthesis of alcohols, we need a compound containing an OH nucleophile here. So NaOH, KOH, etc. OH group is needed here. Then alkoxide, it is needed to make an an ether. For the synthesis of ether, we need, say, sodium methoxide, sodium ethoxide, and all this kind of a thing. So how it is being prepared is just like an acid-base reaction here. That is ethanol. It is reacting with a base Na plus H minus. So this is the base here. That is sodium hydride. That is the base here. That is reacting with the alcohol. That is forming sodium ethoxide here. Sodium ethoxide. The alkoxide nucleophile. We need an alkoxide nucleophile for forming an alkoxide. Why we are using sodium hydride NaH here? Because it is a good base. NaH, it is a good base here. That is sodium hydride. It is a very good base. Why? Because the byproduct here it is a hydrogen gas. There is no problem. That hydrogen gas, it will be bubbling out. It will just escape from the reaction mixture. There is no problem of separating the mixture and all this kind of a thing and recovering the product here. That is the advantage of using the base sodium hydride NaH here. Okay, now conversion. How will you convert an alcohol into an ether? Okay, that will be interesting point for you. Alcohol to ether. Slowly we will be just seeing the conversions also. Because here alcohol will be lot of reactions, it will be coming now. Before that, I just want to introduce you to this conversion, little bit of conversion here. So alcohol to ether, how will you convert? So for forming, and first we should form an alkoxide here. Okay, forming an alkoxide, we need sodium hydride, because sodium hydride is a good base. We know that because the byproduct hydrogen, it is a gas that will be just bubbling out of the reaction mixture. There is no problem of separation, etc. So alcohol to ether. Let us see a alcohol. This is cyclohexanol. Cyclohexanol. So we can react it with, say, for example, NaH. First thing is NaH, that is sodium hydride here, and it is followed by CH3, say, alkyl halide. This kind of a reaction. The first one is NaH. Okay, then followed by the reaction with a ethyl bromide. Okay, so what will be the type of reaction here? Let us see. So this is OH here. Okay, so OH, then we have sodium hydride, Na plus H minus. This is sodium hydride here. So this is, we will be having one electron extra. That is why it's a negative charge here. Okay, now here the base will remove the proton from the OH group. Okay, that is the mechanism here. That is, here we can say, see, now this proton will be removed by this base here. Okay. This is how we are getting the alkoxide here. Then from the alkoxide, there will be a proton transfer reaction taking place here. Okay, so we will be getting, what is the kind of product here? This will be O minus Na plus. Plus hydrogen. So this is the alkoxide nucleophile. So we want an alkoxide nucleophile here. Okay, this is the alkoxide nucleophile formation. Now, that is now the next reaction will be the step 2. That is, this is step 1 reaction. And in the step 2 mechanism, this alkoxide nucleophile, it will be reacting with the ethyl bromide here. Correct. Then we will be getting the ether. The mechanism is SN2. So alkoxide nucleophile. So this will be reacting with our ethyl bromide here. Okay. So this bromine will go leaving group. Then there will be, see, like this here. Okay. Then we will be getting what the final product will be, an ether. That is SN2 mechanism here. The ether will be formed here. Here we get O, then we get CH2, CH3. This is the ether formation here. So it is the two-step formation, two-step process for the conversion of an alcohol into an ether here. Okay. So here ultimately we'll be getting Na plus Br minus sodium bromide will be left behind here. This is the mechanism. That is a two-step mechanism for the conversion of an alcohol to an ether. Correct. Now, very important thing is epoxide. Now let us see. So epoxide, we'll be discussing it as an intramolecular SN2 reaction, we can say. Epoxide synthesis. That is a intramolecular, within the same molecule. SN2 reaction. Correct. So epoxide synthesis, when an organic compound, so it contains both a hydroxy group, that is we are talking about halohydrins. Halohydrin means, so halohydrin, that is an organic compound containing an OH group and an halogen atom. That is just like this here. Say we have a halogen and we have an OH group here. So like this, if you are having a compound here, this is a halohydrin. That is, it contains a halogen atom and an OH group on adjacent carbon atoms here. An organic compound containing both a hydroxyl group and a halogen atom on adjacent carbon atoms. Then what will happen? An intramolecular version of an SN2 reaction take place. Okay, then an epoxide will be formed there. That is the mechanism here. Let us see what is this mechanism. So, we have a halohydrin here. Say, for example, say CC. Then here we have X here. Then here we have OH. Like this here. So here we can say your other groups will be there. Whatever is there. Other groups we can just put it here on a wedge as well as on a dash and all this kind of a thing here. Okay. Like this. Now, what is this intramolecular SN2 reaction? That is what we are going to explain here. Now, so this is reacting with a base B. So this base, this will be removing this proton here. Okay. Then this electron pair, it will get shifted to this oxygen. Like this, it will be there. There will be a proton transfer here. Okay, when this proton is transferred, what will be the product here? The product will be like this. So X will be here only. Then we have this is oxygen. It's a minus charge here now. It's a minus charge oxygen. Six electrons here. Okay, now here everything is same. There is no change here. Like this, we can say, now this X goes here. X goes. Therefore, a positive charge, it is developed here on this carbon. Here, when this X goes here, there will be a positive charge developed. Therefore, there will be an intramolecular version of this reaction taking place in this fashion here. The negative charge on the oxygen atom and the positive charge on the hydrogen atom here. Okay. Now here we will be getting the byproduct. Here it will be Hb plus, H plus, Hb plus. It will be the form. That is a byproduct kind of a thing here. Okay. Now okay. Now as there will be an SN2 reaction taking place here. SN2 reaction. So we will be getting the ring formation will be there. Like this, the ring will be formed here. So we will be getting, okay, this is our epoxide here. So this is the kind of a reaction that is synthesis of epoxide. That is when an organic compound, it contains both a hydroxyl group as well as a halogen atom on adjacent carbon atoms, we can say, correct. Then intramolecular version of the SN2 reaction takes place here and an epoxide is formed here, correct. The starting material, that is a halohydrin. Okay, that is a halohydrin. It is prepared from an alkene. An alkene will give you, we can produce this halohydrin from alkenes here. So this is the epoxide synthesis from halohydrins. Okay, so now general reactions of alcohols, ethers and epoxide. What will be the nature of reactions? Briefly, we will just discuss. So what are the type of reactions? General thing, say alcohols. Alcohols undergo substitution, elimination and oxidation reactions and all. Basically, substitution, elimination, oxidation and all alcohols. Main thing reactions here. So alcohols are similar to alkyl halides. What is the difference? Alcohols and alkyl halides. We should have a comparison here. Alcohols also undergo this substitution, elimination and all reactions will be there. Okay, so alcohols are similar to alkyl halides. So both contain an electronegative atom. That is, electronegative atom will be there. So alcohols, it will contain an OH group here and alkyl halides will contain an halogen atom here. Okay, now it is all bonded to an sp3 hybridized carbon atom here. Both contain an electronegative element. It is bonded to an sp3 hybridized carbon atom here. In both cases of alcohols and alkyl halides. Now what is the difference then between alcohols and alkyl halides here? So alkyl halides, the X, it is a very good leaving group, whereas alcohols do not contain a very good leaving group. Okay, OH minus, that is a very strong base, therefore it is a weak or a very poor leaving group. This is the difference between alcohol and alkyl halide here. Alcohols are similar to alkyl halides. Both contain an electronegative atom. Okay, it is electronegative element bonded to an sp3 hybridized carbon atom. Alkyl halides, they contain a good leaving group. Therefore, the leaving group is this X, that is a very good leaving group here. Good leaving group here. But here, it is a very poor leaving group. OH minus, that is a poor leaving group here. Therefore, what is to be done? Nucleophilic substitution. Okay, with alcohol. As a starting material, we can say, we have to displace that OH minus, ROH here. That is a nucleophilic substitution means ROH. This OH is to be substituted, replaced. How it is possible? Because OH minus, it is not a good leaving group. There's a very poor leaving group here. Okay, the substitution is not that easy. Nucleophilic substitution with alcohol as a starting material, you know, the displacement of the OH minus here. This is not an easy job, because OH minus, it is a strong base, and therefore it is a very poor leaving group there. Okay, therefore this reaction doesn't take place here. So here in this case, we have seen, say, alkyl halide, so reacting with a nucleophile here. So this reaction is possible, RNU. Okay, this is a substitution reaction, and X minus, that is a very good leaving group here. Okay, but in the case of an alcohol, ROH here, plus Nu, nucleophile, so this reaction, it is not possible. So what we should do for the alcohol to undergo, because here this OH minus, it is a strong base and a poor leaving group. That is the primary difference between alcohols and alkyl halides here. Alkyl halides contain a very good leaving group, X, that is the halogen atom. Okay, whereas alcohols contain a strong base OH minus, and therefore it is a very poor leaving group there. Therefore, nucleophilic substitution reaction with an alcohol as a starting material, where the displacement of the OH minus is involved. So it is not that easy here. Okay. Therefore, what is to be done for an alcohol to undergo a nucleophilic substitution reaction? What we have to do now, or an elimination reaction. You see, not only the nucleophilic substitution reaction, but also an elimination. That is a beta elimination reaction. So, what we need, the OH group, it is to be converted into a very good leaving group. That is the most important point which you should remember. So, that is this OH group, it is a very poor leaving group. So, only when we convert this OH group into a very good leaving group, OH group must be converted into a better leaving group, then only the reaction is possible. That is nucleophilic substitution reaction as well as elimination, beta elimination reaction. So how it is possible? How can we do this? This can be done by reaction with an acid. Okay, this can be done by reaction with an acid. Treatment of an alcohol with a strong acid. Let us see what will happen. So, a strong acid like, say, H2SO4. That is how alcohols will undergo substitution reactions as well as elimination reaction. Beta elimination reactions are possible. Because OH minus, first we have to convert it into a good leaving group here. So the good leaving group, it can be made, by treatment with ROH. We have to treat it with a strong acid like, say, H2SO4, or we can say HCl, hydrochloric acid, and all this kind of a thing. So what will happen? The oxygen get protonated here. Okay, an alcohol, when it is treated with a strong acid like sulfuric acid or hydrochloric acid, the oxygen atom, it will be getting protonated. So there will be an acid-base reaction again. Okay, so this will transform the OH minus group, that is the hydroxyl group, that is the leaving group, into H2O. That is, H2O means what? It is a weak base. A weak base means it is a good leaving group. Correct. So what will be the type of reaction here? So we will be getting, say, RO like this here. So ROH2 plus, when it is treated with ROH, so when we are treating this thing with a strong acid like sulfuric acid or a hydrochloric acid here, we will be getting a weak base here. So this ROH2 plus, we will be getting a weak base, will be the OH2, this one. This portion, this will be a weak base here. Therefore, weak base means it will be a very good leaving group here. So if the OH group of an alcohol, it is made into a good leaving group, then the alcohols can undergo beta elimination reactions as well as nucleophilic substitution reaction. Therefore, this OH group, it is to be converted into H2O. This is more important point here, by treatment with an acid, strong acid reaction. Correct. So OH group of an alcohol, it is made into a good leaving group. We need a good leaving group here. Alcohols can also undergo beta elimination reactions and nucleophilic substitution reactions here. So in the same way, like alcohols, so ethers also, do not contain a good leaving group. That means ether also cannot undergo nucleophilic substitution beta elimination reactions directly. Okay, that is because this OR group here, in the case of an ether, this OR group, it is a poor leaving group here, poor leaving group. When it is a poor leaving group means the beta elimination and nucleophilic substitution do not readily take place unless we convert it into a good leaving group here. In the same way, epoxides. So epoxides don't have a good leaving group here, but they have one characteristic. Epoxide is slightly different here. So epoxides, even though it doesn't have a good leaving group, they have one characteristic that neither, the alcohols or nor these ethers have that. Okay, so the leaving group in the case of an epoxide, it is contained, say, in the strained 3-member ring. Okay, it's a strained 3-member ring is there, where angle strain is involved there. That is why it is highly reactive. Therefore, the nucleophilic attack, when it takes place, the ring is opened. So nucleophilic attack in the case of an epoxide opens the ring, correct, and the angle strain is relieved. Okay, even though there is no good leaving group, that is the essential difference between alcohol, aldehydes, alcohols, alkyl halides, ether, epoxide, and all this kind of a thing. So epoxide is highly reactive, nucleophilic substitution, etc. takes place very easily, because even though epoxides do not contain a very good leaving group inside there is an oxygen atom over there. Okay, so there is a special characteristic with epoxide. There's a strained 3-member ring is there. This is like this here. Therefore, the leaving group is contained inside the strained 3-member ring. Therefore, it will react very fast. The angle strain, it will be getting relieved there. Therefore, this is a favorable process. Nucleophilic attack becomes favorable there. How? So this is the kind of a thing here. See. So here you have your other groups are there. Now we have a nucleophile here, a nu minus. So this one immediately it will react here. Correct. So this ring, the ring will break because of the angle strain there. It's a wedge only. Okay, so this one, when it is reacting in this fashion, what happens? What will be the type of leaving group? Let us see what is the type of leaving group here. It will be interesting. So the nucleophilic substitution takes place fast here, like this. So see, this nucleophile is getting, it is attacking this positively charged carbon over here. The rest of the groups will be like this here. This ring cleavage will take place. Okay, this oxygen, there is an inbuilt oxygen here, minus charge here. So this will be acting as the leaving group here. Okay, this O minus. So this one, this will be we can call it as a leaving group because of the angle strain. Angle strain is getting relieved here. So the nucleophilic attack, it becomes a favorable process there. It is a favorable process because of the relieving of the angle strain here. The nucleophilic attack is possible and we get an O minus. So this kind of a possibility, it is not there in the case of alcohols and ethers there. Okay. Now, I will just tell you briefly about the reactions of alcohol. We will not go deep into that. So we will be seeing it only in the next class. So dehydration reactions. What is meant by dehydration? Dehydration opposite of hydration. Okay. That is, one is removal of water, other one is addition. Correct. So let us see. Alcohol dehydration of alcohols. It will form an alkene. Dehydration of alcohols. It will be giving you an alkene. Double bond. So now we have seen dehydrohalogenation. Alkyl halides undergo dehydrohalogenation reactions. So it is for the introduction of a pi bond. Alkenes are containing pi bonds. Compounds with the pi bonds that we have seen. Alkenes, alkynes, and all this kind of a thing. So dehydrohalogenation reactions of alkyl halides. It is one way of introduction of a pi bond into a molecule. So there is another way. Okay, for introduction of a pi bond, another way is to elimination. Elimination of water from an alcohol. That is dehydration. In a dehydration reaction is elimination. That is just like dehydrohalogenation. Here it will be minus H2O as against minus HX. That is dehydrohalogenation, and here is the dehydration. Dehydration means removal of water. So elimination of water. Elimination of water, it is a one way at another method for introduction of a pi bond into an organic molecule here. So dehydration means there is a beta elimination. Okay, in with the elimination, you see, beta elimination means like this here. See, say we have a hydrogen is here, then we have OH group here. Okay, so this is the alpha carbon. We know that this is the beta carbon atom. So this is a beta elimination reaction. Elements of H and OH, both the things are getting removed here. We get a alkene here. It's a new pi bond. Okay, so dehydration, it is carried out using sulfuric acid or any other strong acid, we can say. Dehydration is carried out in the presence of, say, strong acid like hydrochloric acid, sulfuric acid, etc. Or even we can say phosphorus oxychloride, POCl3. We use for dehydration of alcohol, POCl3. We can use it. Then we use it sulfuric acid for dehydration. Then POCl3. There's another interesting thing. So there will be a base also in presence of a base. That base will be an amine base. Okay, dehydration is carried out using sulfuric acid or any other strong acid or phosphorus oxychloride, POCl3, in the presence of an amine base. So we will discuss it, what is the role of the amine base and all later. Okay, then there is another thing is TSOH. That is another, that is what is the TSOH here? That is para-toluene sulfonic acid. Para-toluene sulfonic acid. So short form we write it TSOH here. Okay, now let us see an example how this dehydration reaction take place here. Briefly, so if you are having a compound here of this nature here, say Ca3, say CCA3, then we have OH here, then we have, say, CH2H. So like this here. So when we are treating it with a sulfuric acid, say for example, a strong acid, we will be getting an alkene here. That is beta elimination. Okay. Plus water. So this is the beta elimination reaction here. Okay. In the same way, we can use any other alcohol here. Not necessarily cyclohexane derivatives here. So there is a hydrogen over here, cyclohexanol. There is an OH here. So this will be giving you in the presence of, say, TSOH, that is para-toluene sulfonic acid. So we will be getting an alkene here, okay, plus water here. So these are the beta elimination reactions of alcohols. Okay, so here in the case of this thing, the rate of dehydration, that is the order of the reactivity, etc. So it will be, the more substituted alcohols dehydrate more readily. Okay, that is R3COH. That is the rate of dehydration will be. Let us see what is the rate of dehydration here. That is more substituted alcohol, the dehydration will be faster. Okay, so the order of the dehydration reaction will be, say primary, RCH2OH, this is a primary one. Then we have R2CHOH, this is a secondary one. Then we have R3COH, this is a tertiary one. Okay, tertiary. So the rate of dehydration will be in this order from here, primary to secondary to tertiary. It will increasing rate of dehydration. Increasing rate of dehydration here. Now we have seen that set-save rule earlier. So when an alcohol, it has got 2 or 3 different beta carbons. What will happen? Let us see that rule here. That is, in the case of beta elimination here or dehydration reactions, so we are different types of alkenes will be formed. So when 2 different types of constitutional isomers are possible, the more substituted alkene will be formed. That we have seen that rule here. That is the save rule here we have seen. That is, when an alcohol, it has got 2 or more or 2 or 3 different beta carbons. So the dehydration is, then it is a regioselective one. That word we have seen, regioselective reaction. Okay, that is a regioselective reaction, and the more substituted alkene, it is a major product. Correct? The more substituted alkene, it is a major product when a mixture of constitutional isomers are possible there. That is, when a mixture of constitutional isomers, it is possible the predominant or the exclusive product, which will be the one which will be the more substituted alkene. That is, alkene having more substituent groups on the double bond there. That will be formed there. Okay, this is the save rule we have seen. Now let us see the elimination reaction of, one example. Say, for example, let us see this compound CH3. Save rule, how it is being operated here. Let us see one example. Say OH here, CH3, then we can have a CH2, CH3 here. Okay, so this is what is this compound called? This is 2-methyl 2-butanol. 2-methyl 2-butanol. Okay, so how many beta carbons are here? Okay, that is, we are just seeing the elimination reaction here of the hydrogen and OH group from 2-methyl, say 2-butanol here. So we have, this is the alpha carbon here. So this is the alpha carbon. We know that. So this is beta 1 we can say, and this is beta 2. This is again beta 1. These two are identical carbons here. That is, these 2 carbons are identical. Therefore, we are putting it as a beta 1. And here it will be beta 2. This carbon here, it will be beta 2 here. That is 2 or more, 3 different beta carbons are there. Therefore, now dehydration, it will be a regioselective dehydration here. So when in the case of a, say, treatment with, say, sulfuric acid, what will happen here? So when it is sulfuric acid, so there will be dehydration with, say, minus H2O here. So we will be getting a loss of water from alpha and beta 2. If you see alpha and beta 2 here, what will be the type of products here? Now let us see that two different beta carbon, beta 1 and beta 2 here, alpha carbon, we know that. Therefore, now the product, one product formed will be, say, CH3, double bond, then we can say CH3 here. Okay, so this is the beta 2 carbon here. This carbon is the beta 2 carbon. Okay, that is loss of water from alpha and beta 2 carbon here. So we'll be getting this alkene here. So this is a tri-substituted alkene. Okay, this is a tri-substituted alkene. So this will be invariably the major product here. This is the major product here. Okay, so alpha and beta 2 carbon here. This will be loss of water from alpha and beta 2 carbons here. Okay, now the other way, alpha and beta 2 carbon. Now loss of water from H2O from alpha and beta 1 carbon. What will be the nature of the product here? So it can form another product here. What is the type of products here? C, then double bond C, H here. That is a beta 1. It is forming, one hydrogen is removed, eliminated from there. So we have this CH3 here. Then we have CH2, CH3 here. Okay, this is the kind of a product here. So this is a minor product here. It's a di-substituted alkene. Di-substituted alkene, that is the minor product. It's a minor product here. It's a di-substituted alkene here. Okay, that is loss of water from alpha and beta 1 carbon here. Alpha and beta 1 carbon. It will give you this product here, alpha and beta 1 carbon. So this is the alkene being formed here. Okay, so that will be a minor product because that is a di-substituted alkene here. Okay, therefore the Sheshev rule, that is a regioselectivity, is applied in the case of dehydration reaction also. So hope you have understood. So thank you very much for listening.